we're going to have you each give a short presentation, about 5 minutes. Then we're going to open up the floor so you can have a discussion, between the panelists, but also with the audience, both here and online. So those of you on Zoom are welcome to share questions in the chat or use the raise hands function as usual. So I'll invite Emma van Zoelen to present first. Emma is a PhD student at Delft University in TNO, and her work is titled Human-Machine Co-Learning, Reflective Communication for Shared Awareness of Emergent Collaboration Patterns. Pleasure.
Thank you. So this is always a very long title with a lot of terms. So yeah, I'll just give you a bit of a overview of what my research is about, trying to unpack these terms as well. So I'll start with a bit of let's say a story. So when humans collaborate, they're not always immediately attuned to each other, right? They might speak different languages, have different behaviors. So how we deal with that as humans is usually that we both adapt to each other. So we either learn the language, but sometimes we also change the behavior to make sure that the other understands as well. Language is not only about language, right? It's also about these behavioral things. But then what if we talk about human-machine collaboration? We can, of course, wonder, what does this process of like getting attuned to each other, adapting to each other look like if you have not another human, but this machine, robot, AI system in front of you? So the way I look at this is, okay, a collaboration, in any case, in this case, a dyad, you have a human, you have a machine, they both act in the world, and then they interact. And I think what we can say is that as a result of that, there is something that emerges from the adaptation of both systems. And if they have aligned goals, that what is emergent is some kind of coordination and cooperation. Different patterns of behavior that actually enable them to perform the task together. So what my work is about is partly about understanding what does this emergent process look like, but also how can we ensure that positive emergent behavior can be kept. And for that, it's about making some kind of shared mental model such that they can then talk and reflect about these emergent behaviors, such that they can be like, hey, what we just did, that works super well, let's keep it. So in relation to this term co-learning, so how I see co-learning is as first of all, you have this implicit co-adaptation or mutual adaptation that basically always happens in any collaboration or interaction with two adaptive or more adaptive systems. And then you have you need this sort of feedback loop in order to consolidate emergent behavior and to make sure you can keep it or you can use it in different contexts. So that is what I'm trying to, research and design as well. So I'm going to show you a very brief video, and I think then that's the end of my presentation of some experiments that I did. So let's see if I can play this. So this is a Wizard of Oz. Is it not playing? Can I go to the other screen? Maybe I can click it here. Yeah, so this is a Wizard of Oz experiment where someone had to navigate a field with a robot that knew where to pick certain objects and give them extra points. And it was a bit about this leader-follower dynamic. Wait, I'll pause this so I can tell about the other one first. So trying to see how do people deal with this dynamic of of trying to be fast and go to the other end of a field, trying to listen to the robot and see where it was moving to find certain objects, where you could also see that sometimes they kind of wanted to pull the robot and move faster, and sometimes they walk behind the robot, and you can see all these kind of emergent patterns. And then this is another experiment that I did of a virtual task where you have, you see these squares moving. This was an experiment in which actually like a human and an agent had to pick up rocks from the environment. They had some complementary capabilities and they didn't really know how the other was behaving. And again, also try to observe these emergent behaviors. And from that, I'm now trying to design a structure interface interactions that can help them to communicate about these emergent structures.
Thank you very much, Emma. All right. Next, we will have Jakob Schöffer. Jakob is a PhD student at Karlsruhe Institute of Technology, and his work is titled On Explanations, Fairness, and Appropriate Reliance in Human AI Decision-Making. floor is yours.
Terrific. Thank you so much. Hi, everyone. I'm Jakob. I'm a fourth-year PhD student currently at Karlsruhe Institute of Technology, and what I'm presenting is some in-progress work, which is a joint project with Maria de Ortega from UT Austin and Niklas Kühl from KIT as well, who's my supervisor. Let's see. Okay, there we go. So we all know that AI-based decision-making is everywhere, right? But there have been a bunch of very unsettling examples where this is going terribly wrong. For instance, in hiring, in grading, or in policing, or recidivism prediction in that case. And so for that and many other reasons, it is often proposed that a human be the final decision maker for these types of very consequential tasks, right? So this is the setup that we're looking at in this work, where we have an AI that's making some sort of recommendation to a human decision maker, and then the human decision maker is tasked with either adhering to that recommendation or overriding it, basically. And the idea is that the human adheres to the AI recommendation when it is correct, and overrides it when it's incorrect or unfair. And that we would what typically call appropriate reliance. But the underlying machine learning models are often opaque and very difficult to assess, and so the task of discerning correct and incorrect AI recommendation can be very difficult, right? And so that human doesn't necessarily know when the AI is correct and incorrect. And it has been proposed that explanations, or generally speaking, XAI techniques, whatever that might be, could be helpful for that human decision maker. And so in this project, we ask a couple of questions. And so the first one is, how do explanations affect people's perceptions? So that human decision maker, how do they perceive an AI system when they're given explanations? Second question is, what is the relationship between people's perceptions and their behavior? So how do these perceptions translate to actual reliance on AI recommendations? And then thirdly, what is explanation's role in enabling appropriate reliance in human AI decision-making, which is the skill of distinguishing correct from incorrect AI advice? And so this slide has a lot of information, so I'm going to take a bit of time to introduce that. And so what we've done here is we've conducted a user study around predicting people's occupation from short biographies. And so the task was to discern whether a bio belongs to a teacher or a professor. And this is kind of the interface that our study participants get to see. It's a between-subject study, so either people see the type of bio and explanation that's on the left or on the right, and there's a baseline without explanations. And so what we see is that study participants get to see the biography, and they get to see a highlighting of words that are predictive for either occupation plus the AI's recommendation, right? So the AI tells you, I think this is a professor, or I think this is a teacher, and highlights the words that are predictive of either occupation. And what the difference is here, and that's the crux kind of our study setup, is that we have two different machine learning models that make the predictions. On the left-hand side, the AI uses what we call task-relevant words, which are words that are correlated with the predictions, with the occupations at hand. And then on the right-hand side, the AI uses sensitive features such as gender pronouns. But we control for everything else. So really the explanations are the only thing that's different between the left-hand side scenarios and the right-hand side scenarios. And the AI predictions are the same, and everything else is too. And we have 14 of such bios in the task-relevant treatment and 14 in the gender treatment. And what we see is that people's fairness perceptions towards the system are strongly influenced by whether the explanations tell them that the AI uses sensitive features or not, right? So either the task-relevant treatment or the gender treatment, where the different words were highlighted, significantly influences people's fairness perceptions such that they're much lower when sensitive features are used. And interestingly, that perceptions are driving reliance behavior. So whenever people perceive the system as unfair, whenever sensitive features are highlighted, then people override the AI much more often. However, and that's bad news, I guess, is that even though they override the AI more often, they override both correct and incorrect recommendations. So they're by no means enabled to discern correct and incorrect AI recommendations. They just override more when they see that an AI system uses sensitive information. And I brought two implications of that, and then I'm done. And so our work provides evidence that feature importance type explanations, such that the ones that we're employing in this work, which could be Lime or Shep or any other popular explanation technique, is that they do not provide the relevant cues for assessing whether an AI recommendation is correct or incorrect. Secondly, that fairness perceptions, they're not an indicator for appropriate reliance, even though they're often claimed to be in the literature. And that's all I have. Thank you so much.
Thank you so much, Jacob. We can activate your slides up, and then we'll give you a short introduction. Now we have Lingwei Cheng. She's a PhD student at Carnegie Mellon University, and her work is titled "Overcoming Algorithm Aversion Through Process Control. People will use imperfect algorithms if they can, even slightly customize them." Floor is yours.
Yeah, thanks. Hi, everyone. I'm Lingwei. I'll present the work Overcoming Algorithm Aversion Through Process Control. This work is by me and my advisor, Alex Schöffer. So you see the title, that's pretty much what the main finding is. So sort of down here, but I'll go into the detail. Okay, yeah. So we do this research because we believe understanding algorithm aversion is central to advancing responsible AI development. So algorithm aversion, I think several speakers have touched on this before. It's a phenomenon that occurs when humans are reluctant to use algorithm, even though they can perform more superior than human. And one of the reasons why this might happen is algorithms, even though there's a lot of participatory design that's being used in the design process, the algorithms still continue to be mainly designed by third-party researchers and organizations that may not fully understand users' needs and values. So we see this especially in child welfare. There's a systematic study looking at how child welfare caseworkers make decisions versus how they interact with the algorithms. And it has been shown that caseworkers typically diverge from algorithms' decision when they perceive the algorithm to be punitive, or if they assess care histories, differently than algorithms. So, and there's also a lot of work from CMU's human-computer interaction schools looking at this, where they go in and they interview caseworkers, and caseworker, tell them, hey, we actually often override those decisions. So this can be a problem when algorithm aversion limits the utility, usability, and take-up of the algorithm's decisions. And yeah, so in addition to that, there has been, I think, at least several systematic literature review looking at why this happens. I think one of the paper was suggested by Guy earlier. The Britain one. Yeah. So, so they give many different reasons and frameworks about how you might think about the problem. And the element we decided to focus on is human involvement or decision autonomy. So this theory stipulates that increasing human autonomy could mitigate algorithm aversion. Okay, so we break this human involvement down into two different parts, outcome control versus process control. So outcome control is the ability to modify the outcome of a decision once it has been made. And then process control is the control over the process that leads to the algorithmic tool. So you can think of this as data curation, deciding what kind of training algorithm procedure to use, or what kind of input that should go into the algorithm. So I just want to emphasize that this is not a participatory design study. We're really focusing on the characters of the interactions. So sort of more abstract interactions. So to do the study, we employ a replication and extension model. We ran 3 RCTs, both on mTurk, and we replicate study 2 and 3 on Prolific to double check robustness. So study 1, if you're familiar with the literature, there has been a really influential study by Divorced et al., where they allow participants to change the algorithm's decision by up and down 10%. And then they show that people are more likely to use the algorithm if they have that control over the decision. So we want to replicate that finding and also use it as a comparison baseline for process control. And then in study 2, we administer our process control. And then in study 3, we test if there's any interaction effect between the two types of controls. Okay. So this is just kind of a screenshots of what we allow people to do. So we allow them to either choose the input, so deciding, what factors you should consider when we try to predict a student's test scores, or we allow them to choose the algorithm. So here we kind of write up very, simplified explanation for how algorithms work. So we consider, say, logistic regression, decision trees, KNN, etc., and use a lot of data visualization. So the goal is not to make sure that they understand exactly what the algorithm is doing, but they understand it just enough. So when we talked about the pros and cons of each algorithm in terms of complexity versus explainability, for example, hopefully they can agree with those and make decisions based on that. Okay. So yeah, that's just a summary of each study. So in study 1, we have the can change outcome, use freely, adjust by 10. Basically, don't allow people to make any design decisions, but they have some control over the outcome. And then in study 2, none of the people can change the output. So, they will be asked to decide if they want to use the algorithm or not. And if they decide to use the algorithm, they cannot modify the outcomes. But there are 2 groups where they can change the input and the algorithm, the training algorithm. And lastly, in study 3, it's just like study 2, but now they can decide how they want to use the decision that's recommended algorithm. Okay, so yeah, 4 main research questions. Are they more likely to use the algorithm if they can modify the prediction? Are they more likely to use it if they can change the model? And, how do those effects compare and how do they interact with each other? Okay, so yeah, everything is sort of in the bar chart. So I'll kind of talk through the result. So, I think in terms of the graph, you just need to focus on the first row where we look at the outcome in terms of percentage of participants who choose to use the algorithm. And the gray line separates each study. So the first 2 bars, for example, represent study 1, the panel in the middle, study 2, last panel, study 3. So in the first study, when we look at the blue versus the green bar, we can see that we sort of, mostly successfully replicate the results of outcome control. So the green bar where the participants can change the outcome by 10%, up and down 10%, the participants are more likely to choose the algorithm. However, we say that we mostly successfully replicate the result because if you look at the blue and the red bar, those are actually exactly the same conditions. They're just called slightly differently because they served as the control group for their own separate studies. So it's kind of strange because we should get about the same magnitude of result for the blue and the red. However, we did not see that. So given that the red bar is exactly the same as the blue bar condition, if we control the green to the red, right, then we don't really see this significant effect of allowing people to change outcome. So in that way, we kind of have to qualify saying we mostly replicate the results. And I think the reason why there's such a big difference is because we ran the studies sequentially. So we might be getting a very different cohort in study 2 versus study 1. Okay. And then in terms of study 2, we see that given the outcome control, change input does not increase their likelihood of using the model, but change algorithm does. So as you can see, the purple doesn't differ significantly compared to the red bar, but the brown sort of does. And this is especially significant when you think about the blue bar in study 1, which is exactly the same condition, right, as the red one. And then for study 3, we find that there's no additional effect of providing both controls. And this is shown by the fact that the green, gray, and yellow bars are indistinguishable. So giving people more control does not necessarily make them more likely to use the algorithm. You just need to give them some sort of control. Okay, yeah, so in conclusion, we mostly confirm prior findings on mitigating effects of outcome control. And then we show that the process control in the form of choosing the training algorithm mitigates algorithm aversion, but changing the input does not, which is a little bit of surprising finding, given that there's been a lot of work on feature engineering and how that could lead to, people with more willingness to use algorithms. And we find that giving both outcome and process control does not reduce algorithm aversion more than providing either outcome or process control alone. And lastly, I think it's a very important point because we conducted our study on 2 different platforms and they're exactly the same. But we got very different results on 2 different platforms for qualitatively the same, but quantitatively very different results on the 2 different platforms, and also just throughout different batches when very similar conditions were being run. So given that there's been a lot of existing concerns about replicability in HCI, we just want to highlight that and say that our study serves as a cautionary tale. Thank you
very much. Right, we'll quickly invite you to come up here, and we have time for 1 or 2 questions, that can be from you all, that can be from the audience, or it can be from me, because I've got a question. Yes.
Yes, I do have a question, and Jakob and to
Lingwei?
And but Jakob, right at the very beginning of your presentation, you were saying that with that first that if there was a recommending system, that a human being would either dismiss it or take it on board.
Mm-hmm.
But then also when you've got that she basically said, well, wait a minute, if you can adjust it, you'll be able to do it. So I was just wondering if both of you could have a conversation, about your different findings, given that one is quite absolute and binary, and the other one is actually determining something different.
Yeah. It's a question of what type of decision-making task you're looking at, right? I mean, we are just looking at a binary decision, and so naturally, if you don't adhere to the AI, you override it. So there's just these 2 opportunities. But if it's a regression task, you have to, estimate house prices or something, then adjusting is a lot more meaningful, right? Because in a binary decision task, you can either just go with the AI or not. So I guess it's a question of what type of decisions we're looking at. And we're just looking at this very simplified setting, and I think Lingwei probably had others.
Yeah, sure. So I think there's been some recent studies showing instead of algorithm aversion, there's this algorithm appreciation phenomenon where people are more likely to take the algorithm's advice. And I think some reasons has been suggested, maybe depends on the characteristics of the task or the interactions. And I think there's one study that came out last year that was trying to sort of find a framework that incorporates and explains both phenomena. And I think the way I tend to think about it is not they're absolutely different, but maybe there's a set of factors that you can find, and then you can dial them up and down to lead to either aversion or appreciation. So if there's a set of factors that you can find that you can successfully manipulate, leading to either one, then I think those are the useful kind of key. Yeah. So the fairness one, I think it kind of depends on to what level maybe you can create that type of perception. Yeah,
true. There's a much more nuanced way of looking at it, obviously, where you have scenarios certainly where people contradict the AI. They're like, this can't be right, so I have to override it no matter what. Or situations where people just ignore it and make their own decision, right? And these are different behaviors, even though in our framework these would be subsumed under the same category, basically, of disagreeing with the AI.
Jakob, in your setting, no, you did a choice consisting in considering that there are correct and incorrect answers. What happens if any answer is correct? In the sense that if it is a matter of subjective preference, there is no correct answer. So I override what I am recommended because I don't like it. But there is no correct answer.
Yeah. And again, we're looking at a specific type of decision making, which is a diagnostic task, I guess. So we have a ground truth and we have to diagnose it, basically. So we know what's right and people have to say it is that, and then it's right or wrong. But what you're referring to is like a different type of decisions, right? Where there's no ground truth. And in such cases, it's an entirely different premise, right? And I'm not sure how our findings would generalize to that. In any kind of predictive task where there's no ground truth at inference time, giving out loans, for instance, at inference time, it's totally unclear what's right and what's wrong. This would have certainly implications for
yes, but when you reason in terms of fairness, fairness is very often a matter of subjective appreciation.
Absolutely.
So it's not related to the ground truth.
Absolutely.
You know? So
could be,
if this is the case, it could be that your findings would certainly apply in the case where there is a ground truth in which you have to predict, in which you have to understand whether the prediction satisfies a standard of whatever. But it will not apply, and perhaps it could make sense to reason in terms of fairness to explanation, no? Exactly in the case where your prediction has to do with what is the preference and not what is the ground truth.
Yeah, absolutely. I mean, there are many notions of fairness, of distributive fairness. Specifically, we're referring to notions of distributive fairness that are tied to error rate disparities, where we have different mistakes made for women and men, for instance, and different types of errors, false positives versus false negatives. But there are other notions of fairness that are maybe not even quantifiable, like very subjective.
Yes, but even if you have a statistical notion, no? For instance, you recommend the clerk to give or not a loan to somebody who asks for a credit. No? You can verify that it is biased towards women, so it will have a higher acceptance rate for men with respect to women. But this is not related to ground truth. This is related to the fact, for instance, that statistically, for the same type of features, men have a higher salary than women. So they have a higher acceptance rate.
So we're going fair ahead of time. So I might suggest this particular conversation, maybe the tea break, which is just have it. I want to ask if anyone has one last question for Emma, because she has been very kindly waiting this whole time. If not, I have one. Yeah.
Yeah, I'd like to hear more about how you saw that the humans mainly adapted to the world, to give the walking task.
Yeah, so the task specifically was to get from one side of the field to the other as quickly as possible, so they lost points for every second that it took them, but that hidden objects in the environment could provide them with extra points, and that the robot knew where those were. So basically, if you, as a participant, would do nothing, the robot would just navigate to all objects, but that would like deviate from a straight route. So it was basically trying to balance between following and like taking longer and picking up the objects, or going straight and missing the objects, or something in between. So in the experiment, people did this 4 times with different maps. And so you can see that some people just always follow, some people always lead, but most people over time try to develop some kind of balance. So for example, where they would wait and see like, where is the robot going? And then once the robot had picked a direction, they would like run to the front and then pull the robot towards that direction. So really like seeing, okay, what does the robot do? I want to use its knowledge, and then but I can kind of encourage it to be faster. So I will pull and run. And there were many kind of complex patterns of collaboration, let's say, like that emerged, where you couldn't really say one was leading, one was following, but where they were trying to really make a balance between the two.
All right, let's thank all of our speakers, please.